Today we're going to extend our discussion of integrals up to this point. Let's kind of add that to our notes. Up to this point, all of our integral calculations have been one where we have a function f, and I'm calculating the area between f and the x-axis. Well, if you notice the title of today's lecture, it says areas between curves. So today, we're going to have a function f up here and a function g down here, and we're going to calculate the area between them, which is not hard. It just involves subtraction. Do you see why this is just a subtraction problem? If I know the area, let's say that the red is the area between f and the x-axis, and let's say that the pink is the area between g and the x-axis, right? Then I'm just trying to find this in here, which means I need to subtract. So the definition is just that the area is going to be the integral from a to b of f of x minus g of x dx. Okay, so we're just going to subtract the bottom function. Do you think that's important? Sure is. We need to know which one is the bottom one and which one is the top one. Okay, so we might want to make a notation here. G is the bottom, F is the top. Okay, so let's get to some examples. Let's find the area enclosed by y equals 2 minus x squared and y equals negative x. Now, that's all we're given. So we have to know some things about these graphs. Fortunately, these two are old friends of ours. 2 minus x squared is just an upside down parabola through 2. Okay, there's 2 minus x squared. And the other function is just our old plain linear function through the origin, but it has a negative slope. Okay, so we're going to have negative 1. Its slope is negative 1. So it's going to go through the origin, go through this point, and look something like that. So this one is y equals negative x. So I think you can see the region. Part of the deal on these problems is being able to understand what region I am looking for and which function is on top and which function is on bottom. Isn't it pretty obvious to see which one's on top? In this case, 2 minus x squared is on top. So we can even go ahead and set up our integral. The integral will be 2 minus x squared minus, don't forget that minus sign, minus the bottom function, which is negative x dx. Very important that you remember the minus sign. Very common mistake. Now, don't I need limits of integration? I need limits of integration, don't I? Question mark, question mark. Where are the limits of integration going to come from? Aren't they going to come from these points of intersection? Can I do that algebraically? Yeah. Definitely, especially in this case. The points of intersection are where 2 minus x squared equals negative x. I just set them equal to each other. Now, if it were me, I'd take everything over to the right side so I can work with nice positive x squared. So I have 0 equals x squared minus x minus 2. And what do you know about that? That's a nice little quadratic that will factor, make us feel good about ourselves because we can factor x, it's going to be negative 2 and plus 1. Using the zero product property, I can set each of those equal to 0. You all know how to do that. X minus 2 equals 0, so x equals 2. Set x plus 1 equal to 0, so x equals negative 1. 2 and negative 1 are my limits of integration. Now I've got everything that I need to do the problem. I know that my limits of integration are from negative 1 to 2. So if it were me, I would rewrite this problem, taking care of that little negative issue at the end. So let's do that. It's going to be the integral from negative 1 to 2 of 2 minus x squared plus x dx. And fortunately, this is just a nice little polynomial that we can use the power rule on. I've got 3 integrals here. Just basically 3 integrals. This will be 2x minus x cubed over 3 plus x squared over 2. There's my antiderivative. And we're going to evaluate that thing from negative 1 to 2. So if I plug in 2, I have 2 times 2, which is 4, minus 2 cubed, which is 8 over 3, plus 2 squared over 2, that's 4 over 2, which is 2. There's the first part, minus, putting in negative 1, 2 times negative 1 is negative 2, minus, negative 1 cubed is negative 1/3, so I'm subtracting a negative 1/3, plus negative 1 squared is 1, so this will be plus 1/2. So over here I've got 6 minus 8/3. This is going to become a plus 1/3. But I'm subtracting everything in there, so this is going to become plus 2 minus 1/3 minus 1/2. Okay, and just for the sake of time, I'm going to go straight to the answer, which is going to be 4.5. Okay, we know that we could do some fraction work there and calculate that. Okay, let's do another one. How about the area between y equals secant squared x and y equals the sine of x from x equals 0 to x equals pi fourths. Now, secant squared shouldn't scare us. Okay, let's just kind of do a little review of that because it's good to keep our pre-calculus skills alive and active. Isn't secant the same thing as 1 over cosine? Right? So, and didn't we graph secant by making the hills and valleys meet? Remember, we would graph cosine. You know, cosine would look like this. Right? And then we would make the hills and the valleys meet. So there would be regular secant. They'd meet right there. There would be regular secant, and we would have asymptotes. Right? Okay. Now, this one is secant squared. So what does that change? Well, that just means, can I ever have a negative? And doesn't it make the values a little bit bigger? You know, isn't this value right here, if it's the base one, isn't this 1? So what's 1 squared? 1. So it still goes through here. If I'm doing secant squared, it just means that this thing's going to be a little bit steeper. And it means that this thing right here isn't going to be down there. It's going to be up here, right? So, and we could find this out on the graphing calculator, but it's good for you to remember that analytically. So, what am I finding? Now that we've got secant squared sketched. Now, by the way, this is important. What is this asymptote right here? What value is that? Pi halves. That asymptote is at pi halves. Okay? Are we even concerned with pi halves? So we don't have to worry about that asymptote. We're way before that. So really all we have is this little deal right here. All right? So let's I'm going to clean this up a little bit. I've got basically what looks like a parabola now. Okay? And this is my secant squared. And we're finding the area between secant squared and, wasn't it sine? Well, sine, we know what it looks like. It looks like that. Now, for sine, isn't this first maximum at pi halves? So we are only going from 0 to pi fourths. So it's just this location right here that we're talking about. And if I can just draw a straight line up to the secant squared function, I now see where my area is between the two functions. Okay? So now we're ready to evaluate this, and the nice thing about this one is I have my limits of integration already done for me. So it's going to be the integral from 0 to pi fourths of the top function, which is secant squared x, minus the bottom function, which is sine x, dx. Now, thinking antiderivatives, do you remember what you took the derivative of that got secant squared? Tangent. Right? So when I do an antiderivative of this, this is going to be the tangent of x minus the antiderivative of sine, which is negative cosine. So this is basically tangent x plus cosine of x evaluated from 0 to pi fourths. All right. So let's just do that. Let's go ahead and finish that one. So I'm going to do the tangent of pi fourths plus the cosine of pi fourths, and then I'm going to subtract the tangent of 0 plus the cosine of 0. And all of these, conveniently, are memorized values. The tangent of pi fourths, well, if you remember that tangent is sine over cosine, and if you remember that sine and cosine both have the same value at pi fourths, then you can remember that this one is 1. The tangent of pi fourths is 1 because sine and cosine both have the same value there. The cosine plus the cosine of pi fourths, which is like the cosine of 45. Does anybody remember that one? Radical 2 over 2. And then we're going to subtract the tangent of 0, which remember tangent is sine over cosine, and sine of 0 is 0, so this is 0, plus the cosine of 0, which is 1. So when you simplify that, the 1's go away, and I'm just left with radical 2 over 2. There's my area. All right, let's look at another one. Find the area in the first quadrant bounded by y equals the square root of x, the x-axis, and y equals x minus 2. This is one of those that has, something interesting going on that we have to deal with, and we really can't see what that is until we look at the graph. So I have the graph of the square root of x. Here's the square root of x. We remember what that looks like. We're also bounded by the x-axis and this little linear here, x minus 2. Well, what's the y-intercept of that linear? Negative 2. So it intercepts right here. It has a slope of 1. So it's going to go up 1 over 1, up 1 over 1 to 2. And then it's going to keep doing that. Up 1 over 1, like so. I know it's not the straightest thing in the world, but this is why that little statement about the x-axis is important. Because the region I am looking at is this. Now, if I were to do this problem, the way it's set up now, I would have to do it in 2 pieces. Do you see why? Because I would have to split it right here. And the reason I'd have to split it right there is because this region here is just a regular integral, and this region here is between 2 curves. Does everybody see that? The region on the left, the green one, is just a regular integral. But the region on the right, the orange one, is in between 2 curves. So if I wanted to do this problem the way it is right now, I would have to do the integral from 0 to 2 of the square root of x plus the integral from 2 to what? Well, wouldn't I have to do some algebra to find out this intersection point up here? So you'd have to do some algebra, and you'd have to do the integral of the square root of x minus x minus 2 dx. And if it was a calculator problem, where the calculator was okay, can't I calculate this up here with the graphing calculator? Of course you can. But you also need to know how to do it analytically. Now I'm going to stop right there because this is one method to do this problem. But there's an easier way. Okay, you can do the problem this way. All right? This is long. And you can definitely do it that way. There is a shorter way. The shorter way is to do it with respect to y instead of with respect to x. Now watch how easy this is. We are going to take both of our functions, y equals the square root of x and y equals x minus 2, and we're going to solve them for x. So if I solve them for x, wouldn't I square both sides here? Square root of x squared equals y squared, and I find out that x equals y squared. There's one. This one, I just add 2 to both sides. So x equals y plus 2. Now, how do I look at this graphically, though? It's really not that bad. What we're going to do is we are going to take this original graph and we are going to rotate 90 degrees counterclockwise. We're going to rotate it 90 degrees counterclockwise. Now notice, there's my x, there's my y. So we're going to rotate this exactly 90 degrees so that the graph, looks like this. All I did was I took the original graph and rotated it 90 degrees. Did everybody follow what I did? So now notice, this is the y-axis now, and this is the x-axis. Okay? Because we rotated it. And this top function is the linear. So this is my y plus 2 that we just solved for. And the bottom one is y squared. And it is much, much easier because now I don't have to break it up into all those separate integral things. What's the top function? Y plus 2. So I'm going to have the integral of y plus 2 minus y squared. Okay? So it's going to be a much simpler integral, and this will be a dy instead of a dx. Now I need my limits of integration. How am I going to find those? How can I find the limits of integration? So how do I find the limits of integration? Well, if I'm looking for this intersection point, couldn't I set the two equal to each other? Right? Set y plus 2 equal to y squared. Now when you solve that, you're going to get a quadratic. I'm just going to skip some steps here. This is going to be y squared minus y minus 2. And when you factor it and solve it, you get that y equals 2 and y equals negative 1. Okay? Well, the limits of integration we wind up using, if you look at these coordinate axes, sometimes you get a little bit confused. Okay? You have to think, what was it originally? Wasn't originally, before it was rotated, wasn't this 2? Okay? So your top limit of integration is 2, and your bottom limit of integration is 0. And then you finish the problem just like any other problem. You just find your antiderivative, plug in your numbers, and do the fundamental theorem of calculus, and you get your value. You would get on this problem 10/3. So it's much easier, the shorter way, to rotate it and do it with respect to y. And we're going to stop there for today.